Hey guys, welcome back to another video. This one we're going to be doing special permutations. And I think I've done most of these before, so it's like 2000 plus rating problems, but I'm going to be doing it in Swift, so, start off with something a little bit easier and then we can go to harder ones. And I haven't done them in a while, so it's not like I remember solutions or anything. Okay, so in this one you're given zero indexed array nums containing positive integers. Permutation is called special if for all indices either nums I mod nums I plus 1 is 0. Okay. So basically, numbers next to each other need to divide each other for all indices. Okay, so adjacent nums need to divide each other. Okay, so 3, 6, 2, so 6 divides 3, 6 divides 2. Same here, 1, 4, 3, so 3, 1, 4. Okay, yeah. Okay, so right away they tell you that there's not a lot of numbers, so that's a pretty big hint that, like, if you want like all permutations, typically it's like DP or backtracking. So basically, if you actually have to build the permutations, then backtracking is probably, because you have to like build them. So then like backtracking makes sense because we just need a count. So backtracking would be like 2 to the 14th roughly or something. Or actually no, it'd probably be like 14 factorial, which is like too big. Assuming like every number divides each other, like, yeah. They are distinct. It's in reality it's gonna be less than that, so maybe backtracking will still pass. But the other version is a because there's not a lot here, we can do a bitmask DP. And so a bitmask basically just tells you, so we'll write some like stuff here. So a bitmask basically we represent like, instead of representing the numbers as an array, we just represent it as a bitmask, which just basically means a combination of zeros and ones. So for example, for 143, like we'll have leading zeros, but the last 3 bits will just be like ones and zeros. And then we could say like 0 means we haven't used it and 1 means we have. So it'll be like 0 whatever, and then we'll have like 0 0 0. So it'll be like this. And if we have used them all, then it'll look like this, and you can basically change things around. And you can get every bit and just say like, hey, have I used this before or not? Okay, so what do we need here? Like if we do bitmask DP, like what would be the, like we obviously need the bitmask, right? So bitmask, which is 2 to the 14th. So I guess, yeah, I'm not sure what 2 to the 14th is off the top of my head. But I don't think it's a huge number because I think 2 to the 10th is like 1028 or something. Maybe I'm wrong about that. But anyway, so this might be like 10,000 or something. So say roughly 10,000. I don't know, close to that. Okay. I mean, you can also obviously break it down and figure it out, right? So like, it's basically 8 times 8 times 8 times 8. So 64 times 64 is like 3,600 times 2. So like 7K or something. Yeah, so around what I said. So we have a bitmask. What else do we need? So I think the next part is we need to figure out, like, a bitmask tells you what numbers we used, but we don't really know, like, what's the last number. Because when we pick a number, we have to know, like, what's the last one we picked. So we need that as well. And that can be any number in the array. So that's like another DP thing. So basically need bitmask, which is around 10K. Last number, which is only 14. And then we need to iterate through everything left and use that. So iterate is another 14. So this is what, like 10 to the 4, 10 to the 5, 10 to the 6. I think this will like barely pass. Maybe you have to do this bottom up, which will be a huge pain. So hopefully it'll just pass top down. Maybe it's kind of close. So we'll do this top down DP, and then if it doesn't pass, we'll do bottom up. Okay, so going back here. So we need a cache. And in Swift, you can make a cache that's a dictionary, just like Python. You can make tuples, just like in Python. You can make a struct that contains these things. So yeah, maybe you can make a struct, and then that can be the cache or something. Or you can make a tuple. We'll just make a struct, which is basically just like a kind of like a class, except it's a it's not a reference, it's value. So we'll have like data or something here. So we want the actual bit mask. So like int or let bit mask, and this is type int last number int, and that's it. Actually, that's the only state we need. Bit mask and last number. Okay. Then we can make a cache of this. So we can just say like var cache equals, and then the format here can just be like a key will be data, and the value will be int, like this. Okay, and you can in Swift you can make like a helper function in the function pretty easily, kind of like in Python, and because we're only be calling our DP function like in our special perm, we can just do that here, and then that way we have access to all our variables. So yeah, we also need to know like what's the bit mask constant. We can figure that out actually later. So let's just make a DP function. So func DP. So we're going to take in a bit mask, which is an int, and we're going to take in a last num, which is an int. Return an int. Okay, so if the bit mask equals like if everything is full, then we need to return 1. So this is if bit mask equals, so what is like a full bit mask? So it's basically all ones, and how many ones is it? It's the length of num. So let's make another variable here. So like, so actually don't remember how to do power. So there's this nice like thing, so we can just make a new thing. We say like how to do power in Swift math.pow. So this is just like syntax that like this would be pretty reasonable to ask, especially like in an interview if you don't know for sure. It seems fine to me. So let's take a look. Pow. Okay, so it takes a foundation framework, not math.pow. Okay, and it looks like it gives you a double, and then you can convert it to an int. Okay, and I don't think Swift has fast power like Python. I don't think we need it though, so that's fine. Okay, so let's get rid of this. So we basically want like 2 to the count. So if you think about it, like a full bit mask, like let's say we have 3 numbers. A full bit mask would look like this, and this would just be 2 to the 3 minus 1. So this would be 8 minus 1, which should give us this. So it's basically 2 to the length of the thing minus 1. And that's what we want. So, and let's actually just make this variable like here. So let full mask equals, so pow 2 to the 3, not to the 3, to the count, minus 1. And I think we have to convert this to an int. Okay, so if the bit mask is the full mask, it's an error type. Okay, so we screwed something up here. Oh, it can't be count, it's n. How about that? Does that work? Still error type. Double n. Okay, there we go. So pow takes 2 doubles. Okay, there we go. Okay, great. So if bit mask equals full mask, then we just return 1 because this is like a valid permutation. Then we can make the key. So we can say like let key equals data. So the bit mask will be the bit mask, and the last num will be the last num. So basically we can say like if let res equals cache key, return res. So what this will do is it'll just either be null or a value, and if it's a value, then we can return. Okay. Now the next part is we need to actually try every number in the bit mask that isn't on as long as it divides last num or last num divides it. So we can do that next. So we can just say for I in 0 nums count. So basically we need to get this, like, is this thing on or off? So we can just say, like, I guess basically bool, or we can have an if statement as well. So we can say, like, if, so we want one shifted this number, and that will tell us if the bit is on. And I guess we'll have it backwards. So for this 111, like, this will be the first digit, this will be the second, this will be the third. It doesn't really matter. So basically we can say if one shifted right I times and the bit mask. And I think this will be fine. So if this whole thing is 0, I think this will be false. If it's not, or yeah, actually, we need it to be the opposite. So if this is off, so maybe we can do like this. If this means it's off. Okay. Maybe we need like another one. Okay, so if this is off, that means we can turn it on and call DP. And then we also need like a result here. Yeah, so we need a couple things actually. We need a mod. So, and we need a result. And we need to add these things up. So this is going to be like, we need to make a new mask. So let new mask equals bit mask or this. So this will like turn on that bit. Then we can say result equals, or plus equals, or actually result equals result plus plus DP of the new mask. And the last num will be this like current thing, so num's I. Right? And we mod it by mod. Okay, so this will basically, for every number that we can turn on, oh, we need to check one more thing actually. We need to check that last num is divisible by this number, or this number is divisible by, yeah, or this number is divisible by the other one. So we can do that as well. So we can say like, if last num mod nums I does not equal 0, and nums I mod last num. There's probably a better way to write this, but this is fine. It's not equal 0. So if neither of these is modded, then we'll just continue. Okay. Yeah. Okay, so that seems fine. What's an error here? It looks like we have some parenthesis thing. Res right here. Okay, so then finally we just store it in the key. So we can just say cache key equals result and return result. Okay. Then we need to call this function. So we need to pass in a last num. And so a last num we can pass because these numbers are 1 to 10 to the 9th. We can just pass in 1 because everything is divisible by 1, so it would work. So we can say return DP. The initial mask is 0, so we'll just pass 0, and last num will be 1. Okay, so let's give that a try. Cache, solution data, cacheable. Interesting. Okay, so I think you might need to add like a hash or something. So I will ask, this is another one to ask, like, so how do I make this hashable? I think if you use a tuple, it's auto hashable, but I think that this works kind of similarly to Java where you need like a hash code or something. So we'll find out how that works. And I think, so basically hashable is like an interface and then it needs to conform to hashable. But let's see. Use data as a dictionary, make it form hashable. Okay, so because, yeah, so we can use a tuple, like I said. Okay, so it's basically saying because ints are hashable by default, all we need to do is just say it's hashable, and then it should be good. Let's take a look. Okay. Yeah, so basically, I guess if struct has fields that aren't hashable, then you have to make it yourself. Kind of similarly to hash code in Java, except in Java, if you use like a record, it's auto hashable. If you use a tuple, that's basically a record that's auto hashable. But if you make a struct, that's not. Let's actually, I do want to make it with a struct as well, just so we could try it that way. Or sorry, a tuple. So we can basically say here that this will be a key of, or let's actually see how they implemented the tuple. Cache int. Okay, so you just give it the types. So it's going to be like int to int. Okay. And then instead of making this data, we just make the tuple. So I think this is just like this. Yeah. And then basically it conforms to this type. So this cache is a int tuple that returns an int. And this is an int tuple. So then I think it will be fine. Let's see if we screw anything up. Int does not perform cacheable. Okay. So you can use a tuple. Tuples up to 6 elements are hashable. Okay, so we have a tuple, but it's not. So, okay, our cache is still not hashable with tuple. So let's see why. And this is good if you're like learning a new language. That's why I like learning a new language by doing LeetCodes in it, because you can learn like a lot of fundamental stuff. So let's take a look. Struct tuples. There's no way tuples aren't hashable, so. Okay, I think this is just wrong, so we'll just go to the better one. Okay, so errors. How do I make tuples hashable? Okay, let's take a look. I guess I ran out of this thing. I got Anthropic, so maybe I'll try using that. Tuple using this dictionary correct when DP use bitmask key labeled tuple, which does not match int. So it sees them as different types. Fix using an unlabeled type. Bitmask. Oh, okay. So you don't. Oh, I see. So you don't give labels, or you redefine. I see. Do tuples? Yeah. Okay. So basically, yeah. So I knew this before. So you can make name tuples or unnamed tuples. Name tuples is basically you just give them like names for all the variables. So we can just go with the other approach where we can say that will be named. Nice thing about name tuples is then you can get the value. Otherwise, it's some weird syntax where it's like tuple dot to like access the syntax, which is kind of, or the actual value, which is kind of weird. So we'll go with this approach then. Okay, so basically we give it a name tuple and now you can like do stuff. All right, let's see. Bitmask is not hashable. Why is it not hashable? Okay. Let's see what problems we have still. Okay. Yeah, I really wish this Leet thing wasn't bad. I feel like, even though it says it uses like 4.5, it's not very good. Like, if I use cursor or Claude, it's like pretty good. So, hitting small typo. Swift does not allow label tuple types as dictionary keys. It's a different type. You cannot use labels. Dictionary. Let key. You create a labeled tuple. Use an unlabeled tuple. Okay, so I can't use labeled tuples. Interesting. That seems kind of weird. You can use, but only. Okay, if you want labeled tuples, you must declare dictionaries like this. I thought that's what I did, didn't I? Like key equals. Okay, let me just give me correct code with labeled tuples. And I can just compare with what I had. and we'll see what else I can clean up. That's the other thing. If you're like learning a new language, you can ask for like optimizations, and like there might be things that I wrote here that there's just like better ways to write them, and then you learn all these patterns, and then in your actual interviews, like you can use it all. So varcache tuples. So what's the difference between this and what I have? This looks like the same. I mean, so is it like the spacing? No. Okay. So there's probably more. Bit mask, label tuple key. Let's take a look. So key, same. Cached. So what is the difference? Like if I actually just run this, yeah, it still doesn't. So this still gives you this error. So let me just paste it. Okay. Oh, is there anything else that's improved? Oh yeah, you can do power. It doesn't really matter though because the number is really small. So that's another trick of this, but it doesn't really matter too much. So basically, like if we want a number like this, we can basically do 1 shifted 4 times, I guess, minus 1. So that would look like, or 3 times. So it would look like this, and then we shift it 3 times, so it would go here, and then this. Actually, sorry, it's not minus 1. No, it is minus 1. Yeah, so this it actually would be like this. So it would be 1 shifted, yeah, 3 times minus 1 would, so this would be 0, and these would all be 1s. So it's the same thing pretty much. And especially with a small power, it doesn't really matter. So let's see. Here's a working version. You're seeing the error because label tuple types do not get an automatic hashable. So label tuple does not automatically. So you can't. So you can either use struct. Okay, so I guess you can't use label tuples as a dictionary key out of the box, or you can use unlabeled tuples. Okay, so let's just go with the unlabeled tuple, I guess. So we'll just say int. Interesting. And then I think you just make the tuple like this then. So no label, and then basically the way to access these things would be like key 0 and stuff. So I think the best thing is honestly a struct, a hashable struct with keys, and just make it hashable. That seems like the best. Does not conform to protocol hashable. Still? Let's see. Is this fine? Okay, so yeah, this is unlabeled now, so I feel like it should be fine. I don't know what is wrong here. Oh yes, your code's almost fine. It's fine. Pow, taking modulo, using last num. Quick guard. I mean, I don't know if that matters. So they used a what? Array? Oh, pre-compute transitions. I don't think that. Who cares? Well, let's see if this compiles. It does not. Okay, so we can say this still. Still not hashable. Hitting Swift language reality, tuples do not automatically conform. Okay. Okay. So I guess tuples aren't hashable at all, which is interesting. I'm not sure if that's correct. That's the other thing with LLMs are a little bit worse with Swift because Swift's like newer and there's just not a lot of Swift code. Okay, so let's just go back to whatever we had here. Copy that. Okay. Okay, so I was gonna say this is the best approach anyway. We're just making a simple struct. Same thing as like our record and stuff, and you can add other fields and whatever. Okay, so let's talk about the time and space and all that stuff. Okay, so for the bit mask, the number of states it can have is 2 to the n. Yes, 2 to the n. Last num can be n, and we loop through numbers n times. So this is like, you can make some optimizations to make it a little bit faster, but it's basically roughly this. And because it's only 14, like I said, this is like 10K and this is like 1010. So it's fine. Yeah. Space. So we have the cache, which is just 2 to the n times n. Yeah. Okay. And yeah, it's going to be all for this one. So this is, I mean, this works for me for learning new languages, like just do LeetCode in it, learn all the data structures, and ask for optimization. So even from here, I could say like, okay, you know, like how do I make this better? Like, so that's the last place I could say like, clean up this code, no performance optimization, or just clean up this code in ways you can. And then from here, you look at the improvements, and then sometimes they're not improvements. So then you kind of have to just like make up your mind if like, is it better or not? So let's take a look at what it did. Guard n is greater than 0. I mean, this we already know, so it doesn't matter. Okay, so full mask also doesn't really matter because it's only 14. Key int, private. Okay, private, cool. Okay, bit mask. Key. So this is the same. Skip already used elements, same. Okay, so how did they write it? So bitmask I does not equal 0. Yeah, so I think that's what the same thing that I did. Current. Yeah, this is the same that I did. This is the new mask, same. Okay, so basically the same. There aren't really like any improvements here. So I'm pretty happy with what I had. But for a lot of things, you're going to write code. It's going to be pretty sloppy, and then you can find improvements. So yeah. All right, so thanks for watching. See you in the next one.